Hey guys, in this lesson we are going to be starting Unit 7, which is really short. There are only 3 lessons in Unit 7. This is one of them. So you have a Unit 7 test coming up soon, so watch out. We're going to do formula mass in this lesson, which you've actually learned about before with a different name. But we'll add percent composition, which would be new for you, and that's both anhydrous and hydrous. The bookwork associated with this lesson is here, 2789, 14, 16, 18, 20. We'll work on those in class. So make a header on a second page for classwork that has this bookwork there described, and then follow that with an aim. How can we use mass to describe compounds? Under that, we have our do now. Just, copy it down, but don't answer it. We'll do it later. Okay, formula mass. Formula mass is the mass of one formula unit of a compound. And we also refer to it as molecular mass, which would really only technically be okay if it's a molecule rather than an ionic compound. And then other people will refer to this as gram formula mass, and it's just going to be the same thing, except that the unit will be grams per mole rather than atomic mass units, but the numbers will all be the same. So a quick discussion about this idea, about the grams per mole idea, is that whenever we look on the periodic table for the mass of an element, like let's say potassium, you get 39, 0.09 and other stuff. I'm just going to leave it as a whole number like we have before, but you can think of this in 2 ways. You could think of this as one atom of potassium has a mass of 39 atomic mass units. Or you could think of it as a mole. If you have a mole of potassium atoms, which is like a huge number of potassium atoms, if you had a mole of potassium atoms, it would weigh 39 grams. And that's where we get the unit 39 grams per mole. It is not a coincidence that the numbers will be the same with atomic mass units and grams per mole. Chemists designed the units to match up equally in a 1-to-1 ratio. But the units do have different meanings. Grams per mole would be literally grams for a huge number of atoms. And then the AMU would be the mass of just a single atom in this made-up unit called an AMU. So that's why we use the unit grams per mole sometimes for a gram formula mass. Okay, so without even knowing what a formula mass is, we have to be able to calculate it. So let's calculate the mass of a compound such as potassium carbonate. What we're going to need is the masses of each element and their quantities. So let's get to it. The mass of carbon is going to be 12 atomic mass units or grams per mole. Oxygen's mass is either 16 atomic mass units or grams per mole. And in this formula, I see 2 potassiums, I see 1 carbon, and I see 3 oxygens. So I'm going to multiply the masses by their quantities to get the sort of contributed mass for that element. So I got these values, and when you add them up, I think you get 138 grams per mole. Of course, you could also use AMU as your unit because I didn't specifically ask for a gram formula mass. All right, let's do a little bit of class practice here. I'm going to do these each one by one, but you should have a calculator and a reference table out because I intend to have you put in your answers for these on Edpuzzle. So go ahead and start by doing calcium hydroxide. So there's my first one. I can imagine that maybe you might miscount the number of oxygens and hydrogens and not think that there were 2 of each, but the subscript outside the parentheses will remind us that we have 2 of each of these. Okay, next up is this compound, which is a sort of unique hydroxide compound, which is linked up to a hydrocarbon. So go for it. So here's another one. It's 92 grams per mole. However, I think the thing that could be the trickiest on this one is that we have hydrogen in 2 places. So you have to count them both. We have 5 here and 3 here. So that's going to give us a total of 8 hydrogens. And 92 grams per mole is the answer. Okay, next up is this ammonium and phosphate compound, ammonium phosphate. And so for this one, I got 149 grams per mole, and I noticed there were several tricky areas, and they involved that there were 3 ammoniums. So that would give me 3 nitrogens and 12 hydrogens. So there's my 3 and 12. But then the phosphate had a subscript as well, but it only goes for the oxygen, not for the phosphorus. So I only had 1 phosphorus and 4 oxygens. So I got 149 grams per mole. Last up, we have a calcium nitrate compound. Go for it. And there we have it. I got 164 grams per mole. The only part of this one that could be a little bit tricky is that there are 2 nitrates, which is going to give me 2 nitrogens but 6 oxygens. Yeah, that's it though. Great job, guys. So percent composition is it's according to mass, not the number of atoms. But it basically just says that, like, if you have some compound, it could be any compound, let's say water, and I ask you what's the percent composition of oxygen or what's the percent composition of hydrogen, instead of looking at the number of atoms, we're going to look at the masses of those atoms. Because if we really just judged it by the number of atoms, then we could say, okay, for hydrogen, 2 out of 3 atoms are in this molecule are hydrogen, so it's 67% hydrogen, and then oxygen, 1 out of 3 atoms is oxygen, so it's only 33% oxygen. But this isn't entirely fair, because the mass of hydrogen is actually only 1 AMU, and the mass of oxygen is actually a lot heavier at 16 AMU. So is it really fair to say that this molecule, which is, in terms of mass, almost completely oxygen, is it really fair to say that it is only 33% oxygen? So the way we really do percent composition involves mass and does not involve the strict number of atoms in the formula. So we can use our formula mass table for this, or you can rely on the equation that you'll have on the back page of your reference table on table T. It's like a third of the way down, and it says percent composition. And it says percent composition by mass is the mass of the part over the mass of the whole times 100. And the formula mass table is going to help us a lot because it's going to give us, right away, it's going to give us the mass of the part and the mass of the whole, which is super nice. So let's fill in a formula mass table for potassium chlorate, and then we'll use this equation, which will be a breeze. So one thing I want to point out here, because it does matter, is that chlorine's mass is reported as like 35.45 or so, or maybe 35.5. But I just put in 35.5 because I'm not comfortable rounding it all the way down to a 0 or rounding it up to a 36 because it's so close to being in the middle. There's another element like that, copper, I believe, is going to be right in the middle, so don't worry about rounding that one. But I guess what I'm saying is don't over-round things. We'll round it a little bit as long as it's close, but if it's not very close, let's not round it. So from there, I just need to make sure I have the right numbers of atoms in. So potassium, I have 1, chlorine, I have 1, and oxygen, I have 3. So the mass contributions are 39, 35.5, and 48. In total, I was able to find 122.5 grams per mole of potassium chlorate, but if my real job is to determine the percent by mass of oxygen in the potassium chlorate, then I really just need the mass of the part, which is the oxygen, over the mass of the whole, which is the whole molecule's mass, and then just multiply it by 100. So the mass of the oxygen is conveniently already solved for us if we do the table. So now we have 48 grams per mole of oxygen, and we have 122.5 grams per mole for the entire formula. And so I'm able to determine that oxygen makes up 39% of the mass of potassium chlorate. There are going to be some decimals there after the 39, but with a percent, you don't really need to put a bunch of decimals after it. The Regents won't care if you leave it as an integer number. All right, so we can do another example of this for a hydrated crystal, and in case you were wondering what that is, So the reason why the color of that copper sulfate 5 hydrate or copper sulfate pentahydrate changed color is because as it was heated, that well, you didn't see that, but it was being heated. The water that was associated with the crystal structure was evaporating and it was leaving the substance, and that was causing the color of the substance to change. You might remember that hydrated transition metals have fun colors, and copper is a transition metal. As long as it's hydrated, it'll be blue, but if it's dehydrated, it turns white. And if we wanted to restore the blue color, we would just add water. Okay, let's do one more percent by mass, but this time it'll be for a hydrated crystal. So as you can see, I've put in the masses for the sodium, the carbon, the oxygen. But for water, what should we write? It's worth memorizing that water's mass is 18 grams per mole. And the reason for that is that oxygen is 16 and water, or the H's are 2. 2 times 1 is 2. So 16 plus 2 is 18. So you can just go ahead and put that in there for the whole compound. And we have, let's see, 2 sodiums, we have 1 carbon, 3 oxygens, but we have 10 waters. So when you multiply those to get mass contributions, you get 46, 12, 48, and 180. So there is a lot of water in this compound compared to the other parts. So I was able to find that this molecule will have a mass of 286 grams per mole, but my real charge here is to determine the percentage by mass of water in the sodium carbonate. So I only want to know the mass of the part over the mass of the whole times 100. And the part here is water, so that's 180. The whole is the whole thing, or 286. And I need to multiply that by 100 to get a whopping 63%. All right, so copy down these pair-up questions, which we will do in class tomorrow before our bookwork. And also copy down these summary questions. You have my permission to shorten the last one. Just keep all the details intact. Thank you guys for watching, and I'll see you tomorrow.